Right, so today I'm going to talk about how Netflix is really using Java. But maybe if you've been at QCon before, or if you've been reading our tech blogs over the past several years, you kind of already know all this. Because you probably know that Netflix is really just about RxJava microservices with Hystrix and Spring Cloud, and really Chaos Monkeys are just running the show. Well, I'm only half kidding here, because a few years ago this was actually mostly true, maybe except the Chaos Monkeys. But this stack was something that we were building on in the last several years. But things have changed. And quite often I have conversations with people at conferences like this one, where they're like, well, yeah, we're using the Netflix stack. And I'm like, which stack exactly are you talking about? And it's almost never the stack that we're actually using. These are just things that people associate with Netflix because we've been talking about our technology for so many years. But things might have been changed a little bit. So today we're going to bust some myths. We're going to take a look at what we're actually doing with Java. And things are ever evolving. Things are literally just changing all the time. And my name is Paul. I'm in Java Platform at Netflix. Java Platform is responsible for the libraries, frameworks, and tooling that we build around Java, so that all our Java developers have a good time developing Java applications. I'm also a Java champion. I've been in the Java space for quite a long time. And in the past, I've wrote 2 books about Java modularity. I'm also one of the first authors of the DGS Framework. That's the GraphQL framework we use for Java. We'll talk quite a bit about DGS and how that all fits in the architecture. So yeah, that's me. Before we really start diving into JVMs and how we use Java and the frameworks that we're using, we have to understand a little bit better how our architecture has been evolving. And that kind of explains why we did things in a certain way with Java several years ago, and we're doing things quite differently today. So what you should understand about Java at Netflix is that we have a lot of Java. We are basically a Java shop, and every backend at Netflix is basically a Java app. And we have many applications. At the size of Netflix, there's lots of internal applications to just keep track of things. We're also one of the largest film studios in the world, so there's a lot of software being developed just to produce films, basically. Again, all Java. And then, of course, we have what we call the streaming app, which is basically the Netflix app as you probably know it, and that is what we're looking at here. So this screen here is what we call the LOLOMO, the list of movies. And that is just one example of part of an application that is backed by Java. But you should understand that pretty much everything that I'm talking about today, that is true for basically every backend at Java. We use the same architecture now for pretty much all our different systems, both internal and consumer-facing. And we use the same tech stack everywhere. So although I'm giving this example because it's just kind of a nice example to play with, it's kind of much more universal than that. So when I joined Netflix almost 7 years ago, we were in what I call the groovy era. And what you probably know about Netflix, and this is still true, is that Netflix has a microservices ecosystem. So basically every piece of functionality and every piece of data is owned by a specific microservice. And there's many of them, literally thousands of them. What I have on slide here, I kind of just made it up because it kind of makes sense in my head. And it's a much simplified version of what we actually have in production. But think about this LOLOMO screen, this list of movies that we just looked at the previous slide. You're probably familiar with that screen. To render that screen, we would have to fetch data from many different microservices. So maybe there's like a top 10 service that we need, because we need a top 10 list of movies. So that's backed by a specific service. And then there's an artwork service that gives us the images that we show in the LOLOMO, and these are all personalized as well. And there's probably a movie metadata service, which gives us movie titles and actors and the descriptions of movies. And there's probably a LOLOMO service, which is actually giving us what lists to actually render, which again is personalized. Now, let's say that we have maybe 10 services to call out to. it would be hugely inefficient if your device, let's say your TV or your iOS device, would just do 10 network calls to these different microservices. It would just not scale at all, and you would have a really bad customer experience. It would kind of feel like using the Disney app. It's just not ideal. Instead, what we need a single front door for the API where your device is calling out to, and from there we do a fan out to all the different microservices, because now we're in our network, we're on a very fast network, so now we can do that fan out without performance implications. Now we have another problem to solve, because all these different devices, they're actually, in subtle ways, they're all a little bit different. We try to make the UI kind of look and behave similar on every different device, but all these different devices, like a TV versus an iOS device, they have very different limitations when it comes to memory, network bandwidth. So they actually load data in subtly different ways. Now think about how would you create an API that would work for all these different devices. Let's say you create a REST API. We're probably going to get either too little or too much data. So if we create one REST API to rule them all, it's kind of going to be a bad experience for all these different devices, because we always waste some sort of data, or we have to do multiple network calls, which is also bad. To fix that problem, what we did is we used what you call a backend for front-end pattern. So basically, every front-end, every UI gets its own mini backend. And that mini backend is then responsible for doing the fan out and get the data that UI exactly needs at that specific point. And they used to be backed by a Groovy script. So that mini backend was basically a Groovy script for a specific screen on a specific device, or actually a version of a specific device. And these scripts would be written by UI developers, because they are the only ones who actually know what data exactly they need to render a specific screen. Now this Groovy script would just live in the API server, which is a giant Java app basically, and it would do a call out or a fan out to all these different microservices by just calling Java client libraries. And these client libraries are just basically wrappers for either a gRPC service or a REST client. Now, here we start to see an interesting problem, because how do you take care of such a fan out in Java? That's actually really not trivial, because if you would do this like the traditional way, just you create a bunch of threads and you start to manage that fan out with just manual thread management, that gets very hairy very quickly, because it's not just managing a bunch of threads, it is also taking care of fault tolerance. What if one of those services is not responding quickly enough? What if it is just failing? Now we have to clean up threads and make sure that everything comes together nicely again. Again, not trivial at all. Now this is where RxJava and reactive programming really came in, because reactive programming gives you a much better way to do such fan outs. And it will take care of all the thread management and stuff like that you need to do. Exactly because of this fan-out behavior, that is why we went so deep into like the reactive programming space, and we are partly responsible for making RxJava kind of a big thing many years ago. And on top of RxJava, we created Hystrix, which is kind of the fault-tolerant library, which takes care of failover and bulkheading and all these things. Okay, so this made a lot of sense 7 years ago when I joined, and this was kind of the big architecture that was serving most traffic. Actually, it is still a big part of our architecture, because depending on what device you're using, if it's a slightly older device, you probably still get served by this API, because we don't have just the one architecture, we have many architectures, because it's just nicer that way. There's some limitations, although this obviously works really well, because we have been able to grow our member base based on this architecture primarily. But one downside is that there's a script for each endpoint, because again, we need an API for each of these different UIs, and there's just a lot of scripts to maintain and manage. Another problem is that because the UI developers have to create those mini backends, because they are the ones who know what data they need, they have to write those, but now they are in the Groovy Java space and using RxJava, And although they're very capable of doing so, it's probably not a primary language that they are using on a daily basis. But the main problem is really that reactive is just really hard. And just speaking for myself, I've been doing reactive programming for at least 10 years, and I used to be extremely excited about it and tell everyone about it, how great it all is. It is actually kind of hard, because even if I, with that experience, look at a non-trivial piece of reactive code, I have no clue what's going on. And it takes me quite a bit of time to actually wrap my head around, okay, this is actually what's happening, and these are the operations that are supposed to happen, and this is the fallback behavior, etc. It's hard. Now, slowly we have been migrating to a completely new architecture, and that is really putting things in quite a different perspective. And that's all based on GraphQL Federation. Now, for those of you who are not familiar with GraphQL yet, this is like the 1-minute introduction. Comparing it to REST, one really important aspect of GraphQL is that with GraphQL you always have a schema. And in your schema you put all your operations, so your queries and your mutations, and you define them, and you tell it exactly which fields are available from the types that you're returning from your queries. So here we have a shows query, which returns a show type, and a show has a title, and it has reviews. Reviews, again, is another type that we define. And then we can send a query to our API, which is on the right-hand side of the slide. And what we have to do there, and this is, again, really important, we have to be explicit about our field selection. So we can't just ask for shows and get all data from shows. Now we have to say specifically that we want to get a title and the star score on reviews on a show. If we're not asking for a field, we're not getting a field. And this is super important because, again, compared with REST, where you basically you get whatever the REST service decides to send you, we're just getting the data that we're explicitly asking for. It's more work if you specify your query, but it solves the whole problem of overfetching, where you get much more data than you actually need. And this makes it much easier to create a one API that serves all the different UIs. And typically, when you send a GraphQL query, you will just get the result back encoded as JSON. Now, we're not just doing GraphQL, we're actually doing GraphQL Federation to fit it back into our microservices architecture. So in this picture, we still have our microservices, but now we call them DGSs. And that's just a term that we at Netflix came up with. It's a domain graph service. Basically, it's just a GraphQL service. There's really nothing special about them, but we call them DGSs. And a DGS is just a Java microservice, but it has a GraphQL endpoint, so it has a GraphQL API. And that also means it has a schema, because we said that for GraphQL you always have a schema. Now the interesting thing is that we have, of course, many different DGSs, many different microservices. From the perspective of a device, so from the perspective of your TV, for example, there's just the one big GraphQL schema. And the GraphQL schema contains all possible data that we have to render, let's say, a LOLMO. Your device doesn't care that there might be a whole bunch of different microservices in the backend, and that these different microservices might provide part of that schema. Now, on the other side of the story, on the microservices side, in this example, our LOLMO DGS is defining a type show with just a title. Now, the images DGS can extend that type show and add an artwork URL to it. So these two different DGSs don't know anything about each other than the fact that there is a show type, but they can both contribute parts of that schema even on the same types. Now all they need to do is publish their schema to the federated gateway, and now the federated gateway just knows that, well, it knows how to talk to a DGS because they all have a /GraphQL endpoint, that's it. And it knows these different parts of the schema, so if a query comes in where we ask for both title and artwork URL, it knows that it has to call out to these different DGSs and fetch the data that it needs. So on a very high level, not that different from what we previously had, but there's a lot of differences in the details. Now, how does it change our story here? First of all, we don't have any API duplication anymore. We don't need a backend for front end anymore because GraphQL as an API is flexible enough because of field selection that we don't really need to create those device-specific APIs anymore. That also means we don't have server-side development for UI engineers anymore. That's great. But we do get a schema to collaborate on, and that's kind of a big deal, because now we have kind of closed the gap between UI developers and backend engineers, because now they can collaborate on a schema and figure out, okay, what data do we need in what format. And very importantly, we don't have any client libraries in Java anymore, because the federated gateway just knows how to talk to a generic GraphQL service. It doesn't need specific code to call out to this specific API. It's all just GraphQL, and all it needs to know how to talk to a GraphQL service. That's all. And it's all based on specification, on the GraphQL specification. So we don't need specific code to call to a specific microservice anymore. Now we get into how does that change our Java stack? Well, there's really no any place anymore where we need Rx or Hystrix or such things, because previously we needed this because we needed that specific code to call out, okay, I want to call this microservice and then this microservice and at the same time this other microservice. We needed an API for that. We don't need it anymore because that's now taken care of by the GraphQL Federation specification. Now that's not completely true, because the federated gateway itself is actually still using a web client to call the different DGSs, and that is still reactive. However, it is not using any specific code for these microservices anymore. It's actually a very straightforward piece of web client code where it knows, okay, I have to call these 3 services, just go do it, and it's all GraphQL. So it's very simple. All the DGSs and the other microservices in the backend, they're all just normal Java apps. There's not really anything specific about them, and they don't need to do any reactive style of programming pretty much anywhere. Now, before we dive deep into the rest of our Java stack, I want to speak a little bit about the micro in microservices, because there's another thing that people seem to be confused about, how that actually works in practice. So it is true that a microservice owns a specific functionality or data set. And more importantly, that such a microservice is owned by a single team. And that is really the important part about microservices. And this is all even more true with this GraphQL federated architecture, because it's now even easier to just split things out in different microservices and make that all work very nicely. However, don't be fooled by the size of those microservices, because a lot of those so-called microservices at Netflix are a lot larger, just looking at a code base, than like the big monolith that I've worked at many other companies. So some of these systems are really, really big. There's a lot of code there. And of course, when they get deployed, they might be deployed on clusters of thousands of AWS instances. So there's really nothing small about them. That kind of also answers the question, should I do microservices? Well, it depends on your team size. Do you have like the one team that takes care of everything and it's just a small team? If you would add microservices there, you're just adding complexity at that point for no good reason. But if you want to split your team into smaller teams, basically, just because of team size, then it also makes sense to split up your larger system into smaller pieces so that each team can own and operate one or more of those services. Right, time to actually really get into the Java side of things. We now know on a higher level how and where we're using Java, but now we talk about how that actually looks like. We're now mostly on Java 17, and that is about time. And we're already also actively testing and rolling out with Java 21. Java 21 just came out last week officially. And we're just using a regular Azul Zulu JVM, so it's just an OpenJDK build. We are not building our own JVM. We don't have any plans to build our own JVM, although there was a very interesting Reddit thread about claiming that we do. We really don't, and have no interest in doing so. OpenJDK is really great. And we have about 2,800 Java applications. And these are mostly all microservices of a variety of sizes. And then about 1,500 internal libraries. Some of them are actual libraries, and many of them are just kind of client libraries, which is basically just sitting in front of a gRPC or REST service. For our build system, we use Gradle, and on top of Gradle, we have Nebula. That's a set of open-sourced Gradle plugins. And the most important aspect of Nebula, and I highly recommend looking into this, is version resolution of libraries. So, as you know, Java has a flat class path, so you can only have the one version of a library at a given time. If you have more than one version, interesting things happen. And to prevent these interesting things from happening, you really want to just pick one, basically. And Nebula takes care of that. And the next thing that Nebula does is version locking. So basically, you will get reproducible builds that you always build with the same set of versions of libraries until you explicitly upgrade. And that makes it all very reproducible. And we're pretty much exclusively using IntelliJ as our IDE. And in the last few years, we have also invested a lot of effort in actually developing IntelliJ plugins to kind of help developers doing the right thing. So I mentioned we are mostly on Java 17, and that is actually kind of a big deal because this is sort of embarrassing, but at the beginning of the year, we're mostly on Java 8, and Java 8 is kind of old. So why were we still on Java 8? Because we had Java 11 and then Java 17 available for a very long time already, but somehow we just didn't move. Well, one of the reasons is that until about a year ago, about half of our microservices, especially the bigger ones, were still on our old application stack. It was not Spring, we'll talk about that later. It was some homegrown thing based on Juice and a lot of old Java EE APIs, lots of old libraries that were no longer maintained. And at the very beginning, when we started upgrading to Java 11 initially, a lot of these older libraries were just not compatible. And then developers just got the impression that, well, this upgrade is kind of hard and it breaks things and I should probably just not do it. On the other hand, there was also very limited perceived benefits for developers, because if you compare Java 8 to Java 17, there's definitely some nice language features. I mean, text blocks alone are enough reason for me to upgrade. But it's not that big of a deal, right? The differences between 8 and 17 it's kind of nice, but it's not like changing your life that much. Actually, we saw more excitement about moving to Kotlin than we did just upgrading the JDK. Now, when we finally did start pushing on updating to Java 17, we saw something really interesting. We saw about 20% better CPU usage on 17 versus Java 8. Without any code changes. And that was all just because of improvements in G1, the garbage collector that we're mostly using. And 20% better CPU is like kind of a big deal at the scale that we're running. That's a lot of money potentially. And speaking about G1, G1 is the garbage collector that we use for most of our workloads at the moment. We've tested with all the different garbage collectors available, but G1 is generally the best balance where you get like the best balance of trade-offs. There are some exceptions. For example, Zool, which is our proxy, runs on Shenandoah. That's the low pass time garbage collector. But for most workloads, Shenandoah doesn't work as well as G1 does. So although G1 isn't that exciting anymore, it is still just really, really good. So now that we have finally made that big push to Java 17 and we've got most services just upgraded, we also have Java 21 available, which again just came out last week. But we've been testing with that for quite a few months already. And now things really get exciting. Well, the first exciting thing is that if you're on Java 17, upgrading to Java 21 is kind of almost a no-op. It's just super easy. You don't have the problems that we had from Java 8 to newer versions. But there's also just a lot more interesting features. And the first obvious one that I'm super excited about is virtual threads. And this is just copy-pasted from the JEP, the specification from Java 21 or virtual threads. It's supposed to enable server applications written in a simple thread per request style to scale with near optimal hardware utilization. Sounds pretty good. Well, this thread per request style, if you're not familiar with what that means, if you're using something that's based on servlets, so Spring Web MVC or any other framework based on servlets, thread per request is basically what you get. A request comes in, you give Tomcat or whatever server you're using gives it a thread, and that thread is basically where all the work happens or starts happening for the specific request and stays with that request until the request is done. Now that is a very simple style an easy to understand style of programming, and a lot of frameworks are based on that, but it has some scalability limitations because you can only have so many threads effectively running in a system. And if you have a lot of requests coming in, which we obviously have, then the number of threads is just a limiting factor in how you can scale your systems. So changing that model is really important. And the alternative to that is, of course, doing reactive again. So use something like Webflux. But that also gets you in reactive programming again with all the complexities that we already talked about. Now, I think that virtual threads is probably the most exciting Java feature since probably Lambdas. And I think that down the line, it is really going to change the way we write and scale our Java code. And I think that in the end, it is probably going to further reduce reactive code because there's just not really any need for it anymore, and it just takes away that complexity. We have already been running virtual threads in production for the last month or so, kind of experimenting with it a little bit. I'll get back to that in more detail. And then the other interesting feature in Java 21 is the new garbage collector, or the updated garbage collector, I should say, because ZGZ is not new. That was already available in previous versions, but they now made it generational. And that makes it behave more similar to what G1, or give it more of the benefits of what G1 as a garbage collector has. And that will make the ZGZ a better fit for a broader variety of workloads. So it's still focused on low pause times, but it will just work in a broader variety of use cases. And it's a little bit early to tell because we haven't done enough testing with this yet, but we're expecting that ZGZ is now going to be a really good performance upgrade, basically, for a lot of our workloads and a lot of our services. And again, these things are a really big deal where we can save a lot of money on resources. Shenandoah is also now generational, but that is still in preview. But again, we're going to just run with that and see what happens. Garbage collection is really just too complex of a topic to just know that, oh, I drop in this garbage collector with these flags and it's all going to be magic and super fast. It just doesn't work that way. It's kind of a business where you just try things out and then you tweak it a bit and you try it again and then you find the optimal state. We're not quite there yet, but we are expecting to see some really interesting things there. And then finally in Java 21 you just also have a lot of nice language features. And we really get this concept of data-oriented programming now in the Java language, and it is really nice. It's kind of the combination of records and pattern matching and things like that. So Java is pretty nice right now. Right, back to virtual threads. Although I said that this is kind of a big deal and is probably going to change the way we write our code and scale our code, it is also not a free lunch. It's not just that you enable Java 21 on your instances and now by the magic of virtual threads everything runs faster. It doesn't work that way. First of all, we have to change our framework library and to some extent application code to actually start leveraging virtual threads. That's step one. There's a few sort of obvious places where we can do that and already started experimenting. So the Tomcat connection pool. Again, this is the pool of threads where it gives a thread per request. That seems a very obvious place where we can just use virtual threads instead. So instead of using a thread pool, you use virtual threads. We've already enabled that. We're already running in some big services in production with virtual threads enabled. It doesn't automatically make things a lot faster because you need to do other things as well to really leverage it. But it also doesn't make things worse. So we can just safely enable this basically. Sometimes get some benefits out of it. Sometimes it doesn't really change it because it wasn't a limiting factor. But that's something that you should probably start with. Async task execution in Spring. That is, again, just a thread pool. And very often you get blocking code for like other network calls, etc. There anyway. Seems to be a good candidate for virtual threads, so we enabled it there. Then a really big one that we haven't really gotten into yet, but I expect that will be kind of game-changing, is how we do GraphQL query execution. So potentially with GraphQL, every field can be fetched in parallel, and it makes a lot of sense that we would actually do that on virtual threads, because again, this is often blocking code where you do more network calls and things like that. The virtual threads just make a lot of sense there, but we have to implement this and test it out, and it'll probably take a little bit of time before we get the optimal model there. Then we have some other places that seemed obvious. For example, we have a thread worker pool for GPC clients where the GPC calls to outgoing services happen. And it seemed like such an obvious place, like, oh, let's drop in virtual threads there. And then we saw that we actually decreased performance by a few percent. And it turns out that these GPC client worker pools are very CPU intensive. And if you then drop in virtual threads, you actually make things worse. So that's not a bad thing necessarily. This is just something that we had to learn. But it does show that this is not a free lunch. We actually have to figure out where does it make sense, where does it not make sense, and implement virtual threads at the right points, basically. The good news is this is mostly all framework work at this point. We can do it as a platform team, and we can do it in open source libraries that we're using. And then our developers will just get faster apps, basically. And that's good. In Spring 6.1 or Spring Boot 3.2, there's a lot of work being done to leverage virtual threads out of the box. That will come out next month, and we will probably adopt that somewhere early next year. And then there's a really interesting discussion going on on GitHub in GraphQL Java about changing the GraphQL query execution or potentially even rewriting it to fully leverage virtual threads. That is not figured out yet. It's a discussion going on. But if you're in that space, that's definitely something to contribute to, I think. And then for the user code, because all this other stuff is mostly framework code, for user code, I think structured concurrency is the other place that we're going to see a lot of replacement of reactive code, because structured concurrency is finally giving us the API to deal with things like fanouts and then bringing everything together again. Structured concurrency is still in preview in Java 21, but it seems very close to final, so I think it's at least safe to start experimenting with this and try things out. And then a little bit further down the line, we also get scoped values, which is another new specification coming out related to virtual threads. And that is going to give us a way to basically get rid of thread local. And this is, again, mostly framework-related work, but it's just a much nicer and more efficient way of something similar to thread local. Right, so I've already kind of mentioned a little bit that we use Spring Boot. And since about a year or so, we are completely standardized on Spring Boot. So up until a year ago, about 50% of our applications were still on our own, homegrown, not maintained at all Java stack based on Juice and a bunch of very outdated Java EE libraries. And we didn't really make a good push in getting everything on Spring Boot, but all the new applications were based on Spring Boot already. Now, that became very messy, especially because that old homegrown framework just wasn't maintained very well. So we made a really big effort to just get all the services migrated to Spring Boot. That migration was mostly just a lot of blood, sweat, and tears of a lot of teams. It's just not easy to go from one programming model to another one. But as platform teams, we did provide a lot of tooling, for example, IntelliJ plugins to take care of, kind of, where possible, the code migrations and configuration migrations and things like that. But still, it was just a lot of work. Pretty painful. Now that we are on Spring Boot, though, we have like the one framework that everyone is using, and that makes things a lot nicer for everyone. Now we are trying to mostly just use the latest version of OSS Spring Boot. We're currently using 3.1, and to try to stay as close as possible to the open source community, because that's where we get the most benefit. But on top of that, we need a lot of integration with our Netflix ecosystem and like the infrastructure that we have. So that is what we call Spring Boot Netflix, and it's basically just a whole set of modules that we build on top of Spring Boot, and that's basically just developed in the same way as Spring Boot itself is built, so lots of auto configurations. And that's where we add things like GPC Client and server support. That's where we integrate with our SSO stack, so for OutZ and OutN. You get observability, so tracing, metrics, and distributed logging. We have a whole bunch of HTTP clients that take care of MTLS and again observability and integration with the security stack. And we deploy all these applications with embedded Tomcat, which is pretty standard for a Spring Boot application. Now, to give an idea of kind of the features, how that looks like, we have, for example, a GPC Spring Client, and this looks very Spring-like, right? But it is something that we added, and basically this is referencing a property files which describes the GPC service. It tells where the service lives, and it configures like failover behavior, and that way you can just use a Java API with an XML annotation to call another GPC service. And with that you also get things like observability completely for free. So for any request, either gRPC or HTTP, you get observability for free with tracing and metrics and all these things available. Another example is where we integrate with Spring Security. So we can get our SSO color. So you get the user basically that called your service, even if there were many services in between in a call chain. And as I said, we integrate with Spring Security to also do like role-based authentication based on our own authentication models. Now you might be wondering, why are we using Spring Boot? Why not some other more fancy framework? Because of course there's been a lot of innovation in the Java space in the last few years with other frameworks available. But Spring Boot is really the most popular Java framework. That doesn't necessarily make it better, but it does give a lot of leverage when it comes to using the open source community, which is really big, of course, for Spring Boot, and existing documentation, training, and all these things. But more importantly, I think, is just looking at the Spring framework. It has been just so well maintained over the years. I think I started using the Spring framework 15 years ago. And it is quite amazing, actually, that that framework has been so stable and so well evolved, basically, over time, because it's not the same thing as it was 15 years ago, but a lot of the concepts are still there. And that gives us a lot of trust, basically, in the Spring team that also in the future this will be a very good place to be, basically. Now, you might know that a year ago, almost a year ago, Spring Boot 3 came out, and that was kind of a big deal because Spring Boot 3 really just unlocks the Java ecosystem, I think, because the Java ecosystem was a little bit stuck in two different ways. The first reason is that if you look at the open source ecosystem in Java, it was stuck on Java 8 because a lot of companies were stuck on Java 8, and no one wanted to be the first one who would break that, basically. And companies didn't upgrade because everything just worked fine on Java 8 anyway. Now finally, the Spring team has said, we're done with Java 8, Java 17 is your new baseline. So now we force the whole community basically to say, okay, fine, we'll do Java 17. And everything can start moving again. And now we can start leveraging those new language features. And it also makes it possible that although it's just baseline on Java 17, we can actually also start using Java 21 with virtual threads under the hood. And that's exactly what they're doing. Now, unfortunately, and then the second part is the whole mess around Java X to Jakarta. Thanks, Oracle. This is just a simple namespace change, but it is extremely complex for a library ecosystem because a library can either use Java X or Jakarta, and that makes it either compatible with one but not the other. And that's super painful. Now, because the Spring team is now saying, okay, we're just doing Jakarta, now the whole ecosystem can start moving because it has such a big impact, and we finally get past that point that we were kind of stuck on. It is a big chance to get on these new things though. So moving to Spring Boot 3 isn't trivial, and we've done a lot of tooling work to make that happen. Probably the most interesting one there is we open sourced a Gradle plugin that does bytecode transformation at artifact resolution time. So when you download an artifact, a jar file, it will do bytecode translation if you're on Spring Boot 3 from Java X to Jakarta. So it basically just fixes that whole namespace problem on the fly, and you don't have to change your library. And that kind of gets us unstuck. Now, this is a much broader topic, and my coworker Asi just did a session on Spring 1, VMware Explore, and that session is online. So if you want to know more about this upgrade specifically, I recommend watching that talk. I'll skip this. Then I talked quite a bit about DGS, and DGS is not some sort of concept. Graphical Federation is the concept. The DGS framework is just the framework that we use to build those GraphQL services in Java. Now, about 3 or 4 years ago, when we started kind of the journey onto GraphQL and GraphQL Federation, there really wasn't any good Java framework out there that was kind of mature enough for us to use it at our scale. There was GraphQL Java, which is kind of a lower level GraphQL library. That library is great, and we're building on top of it, so this is completely crucial for us, but it's too low level to use directly in an application, at least in my opinion. So what we really wanted is a GraphQL framework for Spring Boot, and basically giving a programming model based on annotations, as you're used to in Spring Boot. And we needed things like code generation for schema types and support for federation and all these things. And that's exactly what you're getting with the DGS framework. Now, I think it's almost 3 years ago, we decided to open source the DGS framework. So it's on GitHub. There's a really large community. There's lots of companies using it now. And it's also exactly the version that we are using at Netflix, so we're not using a fork or anything like that. So it's really evolved really nicely over the last few years. Now, you might be wondering, if you are actually in the GraphQL and Spring space, you probably have seen that in Spring Boot 3, the Spring team also added GraphQL support, which they call Spring GraphQL. And that was kind of not ideal for the larger community, because now the community would have to choose between, okay, do I bet on the DGS framework or do I go with Spring GraphQL? And both seem interesting, both seem great, both have an interesting feature set, but a different feature set. What do I bet on? And I could go and sell you the DGS framework, how that's better and better evolved and faster and all these things, which is right now probably true because we've been around for a little bit longer. But that's really not the point. The point is that you shouldn't have to choose. So in the last few months, we've been working with the Spring team to get full integration between those two frameworks. And what you basically get with that is that you can combine the DGS and Spring GraphQL programming models and its features in the same app, and it will just happily live together. And that's possible because we're both using GraphQL Java as kind of the low-level library. So that's kind of how it all fits together, and we just integrated the framework really deeply. We're still finishing that, and that is probably going to be released early 2024. At least that gives you kind of an idea. It doesn't really matter if you would pick the DGS framework today. It doesn't kind of get you stuck in there and not be able to leverage features coming from the Spring team, because very soon you will just be able to combine both very nicely. And I think that gets me very close to 40 minutes. Yes. And we have a few minutes left for questions.
Thank you so much, Paul. I loved the plugin for G1GC.
Yes, it was a nice talk, Paul.
Thank you.
Are you guys still using Zool?
We are, yes. I didn't talk about Zool, but Zool is sitting in front of literally every request. And so Zool is just a proxy, so it's not. It's doing a lot of traffic control, basically, but it's not the API server that we talked about earlier. Zool sits in front of either the DGS federated architecture or like the old architecture.
Hello. Hi. So, well done talk. You talked about the upgrade for Java having a limited perceived value there. I think that's interesting. I think a lot of enterprises tend to have this mindset of if it ain't broke, don't fix it, we're just going to sit here forever. What did you do to change that perception, or was it just the Spring upgrade that kind of kicked your guys in the butt and made you do the upgrade?
No, actually the main story was the performance benefit. So the fact that we could say that, hey, you get 20% better performance, and it depends a little bit on the service how that number actually looks like and what it actually means, but the number is real. The fact that we could say that, that made a lot of service owners more interested in it, but it also gave leadership higher up just a push like, this is going to save money, go do it. And that was actually the most helpful thing. The Spring Boot upgrade came later and also forces the issue, but it was kind of after the fact.
Thank you.
A lot of advancements to OpenJDK, so from 8 to 17. Did you directly go from 8 to 17?
So we had services running on Java 11 because the plan was 8, 11, 17. 11, we had services running there. It never really took off because there just wasn't enough benefit. So yeah, we mostly went from 8 to 17.
Yeah, and then that's one of the things, depending on the collectors, as he was talking about, there is some impact with respect to stop the world pauses and some kind of background collections that's happening with Chendler and ZGC. So there's a trade-off, but a lot of improvements went into kind of reducing the limit sets and everything like that. So
I guess a follow-up then. So you mentioned that 20% was kind of the push you needed, but how did you even secure the time to actually experiment with that? How did you convince stakeholders to say, look, we're going to spend some time doing an upgrade on some services and then we'll demonstrate the value to you now?
Right. So that is the benefit of having a platform team as we have. So if I look at my own time, I can do whatever I want. If I think something is interesting, this is not true at all, but I make it that way. If I think there's some interesting value to be had in experimenting with garbage collectors, I'm actually not mostly doing performance work. There's actually other folks who are much better at that. This is just an example. If there is potential value in there, we can get the time to just experiment with it and play with it basically, because our time of like 1 or 2 people is like drops in the water.
Thank you.
Thank you very much. Very nice talking and going in depth with what Netflix is doing. So I have a couple of questions if you have time. One is regarding virtual threads. So did you see any difference in the memory footprint between virtual thread versus the traditional one for the same number of request responses? And the second is regarding the GraphQL versus traditional SOAP, because SOAP was superseded by REST back in the days when I would say data was very precious and your network was very important. You could not have a large number of data going through easily. Now the data is cheap, and SOAP has that disadvantage of a schema being going between the client and the server. I see that GraphQL also has the same problem now, that you have to have the query and the schema going between the client and the server. So how you see the REST, SOAP, and GraphQL in that conjunction?
Right. I think SOAP had conceptually a few things right. For example, the fact that there is a schema, that was a good thing, but it was so incredibly hard to use and complex that the overhead of doing the right things was just too much. And then REST went at least the way everyone is using REST, went kind of the other extreme, like no schema, no nothing at all, nothing is defined, you just throw in some data and we're all good. I think GraphQL kind of sits in the middle there. It doesn't have a lot of overhead for developers to implement the schema. It's very easy. It's much easier than SOAP was just from using it. But you do get a schema, and that takes away a lot of the downsides of just having REST without any schema. So it feels like it has found a sweet spot for APIs. Probably if I'm back here in 10 years from now, I'm like, GraphQL, terrible idea. How did we ever get to that? But you know how that goes. Right now it feels like a sweet spot. And I forgot about your other question.
The virtual threads.
Oh, yes.
Thread.
Yes, there is a difference. That is why we have to be very careful about adding virtual threads where we replace like traditional thread pools. Depending on if these thread pools are very CPU intensive or not, it does or does not make a lot of sense. The memory footprint doesn't seem to be a big factor. We haven't seen any significant bumps there at all. But again, this is all very early days and we're just experimenting with everything. So we haven't quite figured it out yet. But it seems to be very straightforward from memory.
And then I was just wondering about your Kotlin usage percentage and what that kind of is looking like.
I don't know the percentage exactly, but it is fairly low. So for a while we had a bunch of teams, including my own team, very excited about Kotlin. The DGS framework itself is written in Kotlin, although it's targeting mostly Java apps. That's my choice. And we have microservices written in Kotlin as well. The only downside that we see with Kotlin is we invest more and more in developer tooling, so IntelliJ plugins and automated tooling based on Gradle to help with these version upgrades with Spring and all these things. That story is much harder for a platform team if you have to deal with multiple languages. Because even for an IntelliJ plugin, even if it's both from JetBrains, you need to write your inspections in IntelliJ twice if you want to use both Java and Kotlin. And it's just a lot more work. So it's just a lot easier for platform teams if everyone is just happily using Java. That doesn't make Kotlin bad though. We have only seen good things about Kotlin, and it works just really well. It's a great language.